Hey programmers, Alvin here. Right now I want to show you the approach for this Tribonacci problem. And so I know you're thinking, why is he having us do basically a ripoff of Fibonacci? Well, I think it's really important that if you want to get good at these algorithm things, then you have to have a certain level of repetition. As the saying goes, one is none, right? So even though, we've just done the Fibonacci problem, doesn't mean that it's completely something that we've mastered. So if anything, this should be a quick little review, right? Of course, I want you to solve this Tribonacci problem recursively. And so let's take a look at the sequence. So here is a few numbers of the Tribonacci sequence. What you'll notice is in this particular problem, like before, I want you to give me back a particular number of the sequence. So imagine that we had corresponding indices for each of these numbers. When it comes to the Tribonacci sequence, we're going to have three separate base cases, right? The 0th number of the sequence is 0, and also the first number of the sequence is 0, and the second number of the sequence is 1. So with those three seed values, we can come up with our general rule. Right? Just like before, to calculate a number of the sequence or the next number of the sequence, you just take the sum of the previous three numbers, right? Or in general, to calculate trib of n, you do the sum of n minus 1, n minus 2, and n minus 3, and there you'll have your final answer, right? So kind of jumping at a particular spot within the sequence, if I took the sum of 4 plus 7 plus 13, that would give me exactly 24. So you should feel right at home in this particular problem. And so let's start to draw this one out. I don't want to skip any steps. And so before we start building this one, let's have some foresight and figure out how to visualize a problem like this, right? And what's great about visualizing it is that at least if we spend some time, sketching out, a structure of the problem, like visually, it can also help us figure out the complexity of this particular problem. So right now, I want to step through calculating the 5th number of the sequence, which should be 4 in the long run. So like before, I'm going to represent an instance of this problem just with a tree. And so my top level problem will be the root of this tree, right? I want to find trib of 5. And I know that I have to break this problem down into 3 subproblems, right? In other words, I can generate 3 children by doing a -1, -2, and -3, respectively. And I'm just going to carry over that pattern for as many nodes as I can. And of course, whenever I hit like a base case, I can't break that node down any further. We know that when it comes to our Tribonacci problem, we have 3 separate base cases, right? Representing these particular return values. So I'm just going to plug in these subresults. So I should have all of these calculated values, right? 0th number is 0, first number is 0, and also the second number is 1. And now I can start reconstructing my sub-solutions, right? So if I take a look at the particular, to the left, the 3 node, I take the sum of its 3 children. 1 plus 0 gives me 1, right? So the third Fibonacci number is 1. And I'll just continue this pattern, right? Every parent node just takes the sum of its 3 children return values. So I get values that look like this. And finally, at the root, I just take the sum of 2 plus 1 plus 1, which gives me a final answer of 4, right? Very similar to our classic fib problem. So this would be a working solution, basically just doing the same recursive code, except we're going to have 3 recursive calls, which makes sense because every call we make corresponds to a branch that we have in this visual tree. However, what's the complexity of this one? It's pretty slow for the same reasons our Fibonacci code was slow before, right? So if you take a look at this particular tree, I can derive the time complexity of it. Because I know that for my recursive code, the time complexity is at least going to be the number of recursive calls that I make. And if every recursive call corresponds to a node of this tree, I have to figure out what the long-term pattern for the number of nodes is in this recursion tree. So I know that the height of this tree is pretty obvious. It looks like it's going to be along the order of n. And how do I know that? Well, if you look along the left-hand path, it just goes 5, 4, 3, 2. And in general, that's roughly n things, right? Now I'll just think about how many nodes are across on every level. At the top level, there's 1 node. And to get to the next level, I multiply it by 3. And I continue this pattern, right? As the tree gets bigger and bigger, from one level to the next, I would continue by tripling the number of nodes, right? Very similar to our Fibonacci problem. And so you guessed it, the complexity of this is 3 to the n. So an exponential, but with a base of 3, right? And it is the case that our space complexity is a pretty reasonable O of n, right? Of course, we're referring to the space complexity due to the call stack, right? And in general, we can figure out the space complexity from the call stack if we draw out the tree, and we can just look at the height of the tree. The height of the tree being basically the number of levels. And there's roughly, 4 levels here. So I guess it's off by 1, even though our input was 5, right? And so to make this one a little faster, of course, we can just notice any duplicate subproblems, right? So same story like we're used to. Take a look at this subtree, rooted in 3, and I have this subtree appearing here as well. And so I want to avoid resolving that subproblem. We're going to use the same strategy as before, but this time I want to use a different word to describe it. Really what we're utilizing here is dynamic programming. So dynamic programming is really a type of problem solving where we utilize any overlapping subproblems, right? In other words, I have the subproblem of calculating the third Tribonacci number, and if I can store that information the first time I solve that problem, I can utilize it later on because I'm probably going to encounter that same subproblem, right? So this is in the family of dynamic programming strategies. And so far, we've been working with memoization. So really, memoization is just one way we can implement dynamic programming. And so if we use dynamic programming wisely, we should be able to forego that duplicate subtree, right? And overall, we'd be looking at an O of n runtime and O of n space complexity if we implemented that correctly, right? And so to implement that, of course, we're going to use some hash data structure to build that memo. So for my Python people, you're going to use like a dictionary. For my JavaScript people, you're going to use an object. For my Java people, going to use a hash map, right? Any fast lookup data structure. And at this point, we have a pretty optimal solution for this Tribonacci sequence, right? It should be able to run in a pretty decent time. And so with that, what I want you to do is give this code a shot on your own. But don't forget, if you get stuck, we do have a code walkthrough available as well. So give it a go.